Hello, everyone, and glad to meet you all virtually today to talk about an important topic of our time right now. What is driving AI, and what are the hardware boundaries to the infrastructure? Spoiler alert, memory is a key factor, and that's what I'm going to focus on today. So, before that, let me give a bit of context from Meta perspective. As you know, Meta has a mission to help people to build community and bring the world closer together. This is done through family of apps Meta has: Facebook, Instagram, Messenger, WhatsApp. And today, Meta family of apps is used by mind-boggling 3.19 billion users on a daily basis and almost 4 billion users on a monthly basis. So we have a responsibility to enable this mission with very efficient infrastructure. Let us connect that goal to AI use cases and eventually to the infrastructure demands. So Meta has two major AI use cases. First is to serve personalized recommendation to the users that make their social experience rich. So the deep learning models that we have provide that personalized experience by training the models and providing the recommendations as an outcome of that inference. Gen AI is creating richer experience for coding and enabling industry overall for other research and commercial use. And all these use cases are growing very fast and changing the infrastructure requirements at a very fast pace. Now let's dig in to see how the infrastructure needs are differing from AI. For AI, as compared to our traditional general compute infrastructure that we have been using in hyperscale data centers for a long time. There are fundamental differences that AI brings to infrastructure as a use case. Now, while general compute applications typically run as a millions of small stateless applications, any of them can fail and the application can survive there. That's how it will work for the traditional use cases. And that's what we optimize for. Whereas the now large AI applications, as compared to that, run across cluster of GPUs or accelerators as a single job. So failure has a significant penalty for an AI job. For example, training job that runs for weeks or months, if it needs restart, even if single GPU fails in the job, then you have a significant penalty because the whole job gets impacted. Performance for AI jobs depends on all the components in the cluster and needs closer hardware software co-design to make sure that we have optimal TCO. One more thing to keep in mind is that many component technologies are platform cadence. That means they run on a general compute that are driven by general CPU roadmaps, whereas the AI needs are growing much, much more rapidly. And we foresee that very fast pace of demands is being placed on the components that enable AI systems. So we are talking about all the system components, all the network components, all the data center components. So overall, the center of gravity for AI systems is now towards GPU accelerators instead of CPU in a traditional compute system. And the exponential growth of AI demand has shifted the data center infrastructure design challenges in a significant way by these GPU-centric designs. Now, ideally, one would like to have one largest accelerator system to run the whole AI job, because we talked about saying that the AI job runs as a single, why not just get one largest accelerator? However, that's not possible because, as the model sizes are increasing, that accelerators need to continue to increase in a clustered fashion. So that cluster size needs is required for the training jobs. Now, there are multiple methods how we can achieve this higher performance by cluster. One could parallelize the tensors or context to run on multiple GPUs. Tightly coupled clusters allow such tensors and context to be run parallel. And then one layers loosely coupled clusters on the top of these scale-up clusters for parallelizing the data and pipelines. So this allows a large AI job to be run on AI cluster by optimizing various parts of executions and make sure that we can achieve the scalability of the performance as we need. Now let's look at what does it take from the network perspective to enable such kind of a scale up and scale out, right? Tightly coupled jobs that use scale up networks, they demand very high bandwidth and lowest latency. There are examples of interconnects today that are load store based interconnects. And you know those, there are NVMe switch, there is Infinity Fabric being discussed, verb based or message based interconnects like Rocky at a very high bandwidth and low latency. And then loosely coupled jobs like data parallel use scale out networks. And they need also higher bandwidth. They need much higher bandwidth than the typical front end networks, but little more lenient as compared to the scale-up networks. These are typically RDMA networks like Rocky or InfiniBand. Higher bandwidth requirements for scale-up networks is pushing the physical limits of distances and driving tightly connected cluster topologies. For example, how do we make sure that, what is the distance that we can drive with a SerDes like 200 gigabits per second per lane or 400 gigabits per second per lane? So this is going to continue to bring the accelerators tighter and tighter together based on the limitations that we run into the distances. Scale-up interconnects carry a lot of memory accesses also, because that's what the tightly coupled systems will do. These are the memory accesses that will run across the fabric, and they drive very high bandwidth and low latency requirements. This also weighs in on the overall system design. Now, for a scale-out network that we talked about, there are additional challenges as we spread the systems to the larger topologies. How do we keep the effective bandwidth for the applications higher by maintaining P99 or the tail latency in check by avoiding all hotspots and the congestion? And this all depends on the workloads and applications also. So let's look at that, what those applications are and how they impact the overall system design. There are multiple use cases. There is a significant diversity in the AI system requirements based on these use cases. They are classified into two. You have training, and then you have a Gen AI, recommendation and Gen AI. And within the recommendation, you have training and inference, recommendation training, reco training, and reco inference. And then for Gen AI, you can have training, and then you also have inference. And then inference you can further granularize by saying prefill, which basically is getting the first token in the LM world, and then decode, which is getting the subsequent tokens. And these use cases have significantly different requirements. So we look at all these use cases, you can see that the system resource requirements for each of these use cases and layering them on top of each other, you can see that various models place very different demands on resources that makes the overall system design optimization for TCO a very challenging job. AI use cases push this envelope for most of these use cases. The need for building larger accelerators, larger tightly coupled systems, as well as growing model size and performance needs are pushing the AI systems and components beyond their traditional growth trajectories. Now let's focus more on the memory part of the requirements. Now, why is memory important and what is exactly driving that? Ideally, we talked about saying that to run a single job, it will be great to have a single accelerator. So I know we said that this is not feasible and we need to run into the accelerators. However, as we looked at the scale up demands, that actually as we continue to grow the models, we want to get each accelerator also to get larger and larger to make sure that the scale up cluster remains in a feasible domain. So there is a strong reason to make sure that we continue to increase the accelerator sizes. So as we increase the accelerator sizes, this will continue to drive the memory capacity as well as the performance for the memory that is integrated in the die to achieve the kind of bandwidth that we need for the GPUs and accelerators. Typically, you have memory that is integrated into the package itself, which is the high bandwidth memory or HBM, as it is very well known. One also has to keep in mind that this increase in size of accelerator comes with additional burden of increasing reliability. Cost of job failure is very high. So although we'll talk about that a little bit later. So bottom line for memory capacity and bandwidth need for the accelerator is that the first priority is make sure that integrated memory technologies like HBM need to continue to grow for capacity, performance, and reliability. Now, as we know, even though we talked about this primary memory that sits inside the accelerator, that we have talked about the memory wall a lot. Model sizes as well as the accelerator performance are driving memory needs beyond the embedded HBM capacities as well as the bandwidth. As you can see in the charts, that's what happens. We are continuing to drive the performance of the GPUs, but the HBM capacities that are coming out as well as the interconnect bandwidth that are coming out are definitely not able to keep up together. So the requirements for this accelerator performance are going way beyond what we are seeing in these charts also. So that's going up dramatically, which will make it even more challenging for the network and memory capacities to keep up with this. So as we're making these large accelerators, the tightly coupled scale-up clusters demand are actually growing exponentially, not linearly. And a higher bandwidth also need to keep up, and we want to make sure that the latencies are maintained low. So this is pushing hyperscale data center to its limits, because as you keep on growing larger accelerators, that comes at the point of basically increasing the power how much you can land it in the power, how many accelerators that you can have it in a single rack to make sure that you can achieve the scale up clusters. So you're looking at accelerator performance, you're looking at memory capacity that it is connected to, what's the performance that we provide for the memory to the accelerators, how many accelerators we land, which basically is going to push the rack power, the network bandwidth to connect such high performance net accelerators in the scale up networks, as well as the scale out clusters. The network latency that we can achieve and how we manage that, types of networks that we support. How do we make sure that the cluster reliability is maintained? That means the cluster reliability of the all the components in that cluster that participates in the job. All of these are pushing the data centers to its limit. However, let me hold my excitement there and keep focus back onto the memory. Now, what are the components of that increase the total memory need per accelerator for the AI job? So at broad categories level, one has activations that are computed during the forward and backward passes. If this exceeds the memory capacity, internal capacity, then typical technique is to recompute during backward pass. That results into accelerator compute and memory trade-off. Model parameters and embeddings are increasing also to a large value and cannot typically fit into GPU's internal HBM memory. However, the access patterns are such that one could use locality and tiered memory accesses with appropriate prefetching techniques that allow right placement across two tiers of memory. And there are additional accelerator memory users like gradients, weights, optimizer states, etc. And these are all contribute to the local memory needs of the accelerator. And as the completion of the job is important in face of various failures, checkpointing also allows restarting the jobs and after failure. And so without losing all the time on the job that was already executed, you can achieve significant improvement by having the checkpoints. Of course, this has memory requirements. And as we start looking into this, there are innovative explorations going on. Basically, how do you make sure that we can do in-memory checkpointing, etc. So these are going to drive the memory requirements even faster than what we have seen in the past. So all of these add up, activations, more, embeddings, gradients, all of this basically add up to the overall memory requirement that is being addressed by the HBM that we already saw was falling behind. So you're looking at capacity that already is falling outside, it's falling behind the accelerator, and we want to make sure that how we provide the tiered memory for that. So as overall memory requirement is not being satisfied, that's what we have inside, which is the HBM. We need to start thinking about memory expansion and the ways we can achieve that. So the next option is basically we start using some kind of tiering. So use HBM as a tier 1 memory, and you have tier 2 memory that is accelerator has access to, which will allow higher capacity at a relatively reduced bandwidth as compared to the aggregate HBM bandwidth that we have inside. But AI patterns potentially will allow us maybe to do this tiering, which uses the HBM for its bandwidth needs and then has the capacity attached to the tier 2 memory to be used as an overall solution, bring that in an appropriate fashion for the AI jobs to use to satisfy the overall requirements that we have for the AI clusters. Now, how do we do this? So the easiest and first preferred option would be you already have a CPU attached to the accelerators in the system, so expand the memory through the CPU. So accelerator can access the CPU attached memory as the tier 2 expansion capacity. You already have the high bandwidth interconnects between GPU and CPU, which is required to match the desired memory bandwidth. So as you put more memory behind it, yes, obviously you need higher bandwidth to make sure that you access that. You have PCIe today, CXL potentially that can be used there. NVLink C2C has been out there now as a new proposed example for how to use such a expansion through memory. Infinity Fabric, they're all well-known examples of this. There have been well-documented examples that if you use the memory attached to the CPU through the attached interconnect between the accelerator and a CPU, one could benefit that. And how to do that with embedding is something that we have been out there and we have put the information out there and demonstrated that also. Now, one could also, if it is within the node, when I say node native, it is within the node which has a CPU and a GPU. One could imagine of expanding that memory within that node by adding the memory directly to the accelerator also, using any expansion interconnect like CXL or any other interconnect that allows the memory connectivity. Now let's dig into what happens to the node native memory, node native memory that is fabric attached. In this case, node native memory that is attached to the CPU or the GPU directly inside the system itself. To achieve this, one needs to make sure that the bandwidth and capacities are addressed at each point of component interaction. Now, the interconnect that is being between the accelerator and a GPU, accelerator and a CPU has to have a high bandwidth without burdening already shoreline limited accelerators. In the sense, you have to provide that bandwidth to make sure that I have smaller number of services that allow me to achieve the higher bandwidth. This means the service has to achieve the desired bandwidth without really putting too much burden on the accelerators. Let's take an example. If one needs to achieve the tiering, which has, let's say, 1/10 of the bandwidth of your tier one memory, which is HBM bandwidth. And if that HBM bandwidth is, let's say, 8 to 10 terabytes per second, the tier two memory has to have 1/10 of that, which is maybe 1 terabytes per second or more. So if you do the math, basically, you want to make sure if you're using CXL or PCIe, you want to make sure, or any other fabric, use as less number of SerDeses as possible, because this is going to continue to increase as we go forward. CXL is, or PCI is challenged here. Higher speeds like PCI Gen 7 will be required to make sure that we can keep up with the accelerator requirements in next few years. And this bandwidth needs, once you go across to the CPU, has to be matched by the number of memory channels that we have on the CPU to match the interconnect bandwidth. So you need the memory channels as well as the speeds on the memory modules that you're placing. So higher speed of the DIMMs and higher speed of capacities are also required to match the bandwidth and the capacity requirements of this accelerator. So this is what will be required to make sure that we can enable that higher capacity, tier 2 capacity, and the bandwidth for the accelerators. Now, one could think of fabric attached. So we discussed the scale of fabric. This has a very high bandwidth. So today, between accelerator to accelerator, you have, in a tightly coupled systems, you are actually using fabric attached memory, which basically means one accelerator can access the memory that is connected to the other accelerator. One could also consider that, you can have a memory attached to the fabric itself. Oh, by the way, before we are good there, the fabrics today that I talked about that allow accelerator to accelerator memory accesses, the examples are well known out there. There are load store interconnects well known like NVLink, Infinity Fabric, and also there are message passing interconnects like RDMA or Rocky. CXL can play a role here. However, as you can see, you need to match the performance and latency needs that the scale-up networks demand. Now, if to enable that, now let's look at what that would mean if you're going to enable the fabric attached memories or the memory interconnect. Now, if you look at here, there are vendor specific technologies today. As we said, there's NVLink, there is Infinity Fabric, these are available. These enable load store accesses. CXL is an open fabric now available that can enable load store accesses to accelerator, as well as the accelerator to memory connectivity. However, CXL lacks these available technologies. We talked about NVLink and Infinity Fabric, as well as Ethernet by at least 1 or 2 generations. And it is also very slow to respond to the fast changing AI demands because it has a large established base of PCI ecosystem. However, this is the open option available today. So if it can address these challenges, then it has a potential of becoming a very interesting option here. Accelerator to accelerator memory accesses are already established for scale-up networks that we talked about today. One could imagine in future adding memory to these fabrics or to these scale-up fabrics because they already have high bandwidth and a low latency, and then can potentially enable future novel use cases like what happens if you can do near memory compute. Can you offload any kind of compute from the GPUs to scale it across to the memories? Potentially a novel use case. In-memory checkpointing that we talked about. These are all potentially allowing you to increase the reliability as well as the performance of the AI jobs in the future. So to summarize, AI is pushing the memory requirements across HBM, across all the DRAM technologies, across all the interconnects for the capacities as well as the interconnects. This is going to require a lot of innovation. We are going to use these technologies, we are going to use these products, and the use cases are going to, AI use cases are continuing going to push the envelope on this. This is going to require new standards, system designs, industry collaboration for such requirements, use cases, benchmarks, and shared knowledge. Various standards bodies are working on this. And a plug for this work being done in OCP is Composable Memory Systems, a large community jointly working on this. So the appeal for all of you is to join hands to address these exciting and daunting challenges by working with the SNIA and JEDEC and CXL and OCP, and make sure that we'll be ready for all the challenges that AI is facing for our infrastructure. Thank you very much.